This transformer installation is not code compliant. The National Electrical Code, or NEC, Article 100 defines a circuit as a conductor or system of conductors through which an electric current is intended to flow. In this case, the neutral bus and ground bus are tied together, creating a single circuit with two paths for current flow. This violates the requirement that circuits be identified and maintained separately according to their purpose. NEC Article 250 requires that the neutral conductor and grounding conductor be kept separate throughout the system. The center-tapped conductor from the transformer should not be used as both a neutral and grounding conductor. NEC Article 450 requires that transformers be installed in accordance with the manufacturer's instructions. This installation does not seem to follow the manufacturer's intended use of the transformer. There are serious safety concerns associated with this setup. Firstly, electrical shock is a major risk. The improper grounding and bonding can create a hazard of electrical shock to personnel and equipment. Secondly, fire is also a concern. Faults or overloads in the system can cause excessive current flow through the neutral conductor, which is not designed to handle such current. This could result in a fire. To make this installation code compliant, one of the following solutions could be considered. Firstly, install a new transformer with a true neutral and grounding system. Secondly, use a single-phase transformer with a secondary voltage of 240/120 volts. This would eliminate the need for a center-tapped conductor. Thirdly, install a ground fault circuit interrupter, or GFCI, on each circuit to protect against electrical shock from neutral ground faults. It is crucial to consult with a qualified electrician or electrical engineer to determine the best solution for your specific situation. It's important to understand the implications of improper electrical installations, especially when dealing with transformers and grounding systems. Let's delve deeper into the specific code violations and safety hazards presented by this setup and explore the alternative solutions in more detail. Looking at Article 100 of the NEC, the definition of a circuit is paramount. The code emphasizes the importance of maintaining clear and distinct electrical pathways. When the neutral bus and ground bus are bonded together, it creates a scenario where current can flow through both the intended neutral path and the grounding path. This creates confusion and undermines the safety mechanisms designed to protect against faults. The purpose of a dedicated grounding system is to provide a low impedance path for fault current to return to the source, allowing overcurrent protection devices like circuit breakers to quickly trip and energize the circuit. When the neutral and ground are combined, it can impede this process, potentially delaying the response time of the protective devices and increasing the risk of electrical shock or fire. Article 250 of the NEC is dedicated to grounding and bonding requirements. This article meticulously outlines the rules for establishing a safe and effective grounding system. A key principle is the separation of the neutral conductor and the grounding conductor. The neutral conductor is intended to carry current under normal operating conditions, while the grounding conductor is intended to carry current only during fault conditions. By combining these two conductors, the system loses its ability to differentiate between normal and fault currents, which can compromise safety. The center-tapped conductor, in this case, is intended to provide a reference point for creating a 120/240 volt split-phase system. However, when it's used as both a neutral and a grounding conductor, it violates the fundamental principles of grounding and bonding. This can create a situation where the grounding system becomes energized under normal operating conditions, which is extremely dangerous. Moving on to Article 450 of the NEC, this article focuses on the installation of transformers. Transformers are critical components in electrical systems, and their installation must adhere to the manufacturer's instructions and all applicable codes and standards. The improper use of a transformer, such as the configuration described, can void the manufacturer's warranty and create a hazardous situation. Transformers are designed to operate within specific voltage and current parameters. When they are used outside of these parameters, it can lead to overheating, insulation breakdown, and ultimately failure. This can result in fire, electrical shock, and equipment damage. Now let's examine the specific safety concerns in more detail. The risk of electrical shock is significantly increased in this situation. When the neutral and ground are combined, any fault current can flow through the grounding system, potentially energizing metal parts of equipment and structures. This creates a shock hazard for anyone who comes into contact with these energized surfaces. The severity of the shock depends on the magnitude of the fault current and the resistance of the person's body. In some cases, even a small amount of current can be fatal. Furthermore, the risk of fire is also a major concern. When the neutral conductor is overloaded due to improper grounding and bonding, it can overheat and ignite nearby combustible materials. The insulation on the conductor can also break down, creating a short circuit that can lead to a fire. Additionally, the transformer itself can overheat and fail, causing a fire. It's important to remember that electrical fires can spread quickly and are often difficult to extinguish. Now let's discuss the alternative solutions for making this installation code compliant and safe. Firstly, installing a new transformer with a true neutral and grounding system is the most comprehensive solution. This involves replacing the existing transformer with one that is specifically designed for the intended application. The new transformer should have a dedicated neutral terminal and a separate grounding terminal. The neutral conductor should be run back to the source, and the grounding conductor should be connected to a grounding electrode system that meets the requirements of the NEC. This will ensure that the neutral and grounding systems are properly separated and that fault current has a safe path to return to the source. Secondly, using a single-phase transformer with a secondary voltage of 240/120 volts is another viable option. This would eliminate the need for a center-tapped conductor and simplify the grounding system. The 240/120 volts transformer would provide a balanced voltage supply for the lighting system, and the neutral conductor would be properly grounded at the transformer. This would reduce the risk of electrical shock and fire. Thirdly, installing a ground fault circuit interrupter, or GFCI, on each circuit is a cost-effective way to protect against electrical shock from neutral ground faults. A GFCI is a device that monitors the current flowing through a circuit and detects any imbalance between the hot and neutral conductors. If an imbalance is detected, the GFCI will quickly trip the circuit, cutting off the power and preventing electrical shock. GFCIs are particularly effective in protecting against shocks caused by neutral ground faults, which are common in improperly grounded systems. It's important to note that GFCIs are not a substitute for proper grounding and bonding, but they can provide an additional layer of protection. In addition to these solutions, it's also important to ensure that all wiring and equipment are properly sized and installed according to the NEC. This includes using the correct wire gauge for the load, properly terminating all connections, and protecting wiring from physical damage. Regular inspections and maintenance are also essential for ensuring the continued safety and reliability of the electrical system. It's crucial to consult with a qualified electrician or electrical engineer to determine the best solution for your specific situation. An experienced professional can assess the existing installation, identify any code violations or safety hazards, and recommend the most appropriate course of action. They can also provide guidance on selecting the right equipment, installing it properly, and maintaining it over time. Remember, electrical safety is paramount. Improper electrical installations can have serious consequences, including electrical shock, fire, and equipment damage. By taking the necessary steps to ensure that your electrical system is code compliant and properly grounded and bonded, you can protect yourself, your employees, and your property from these hazards. In summary, the transformer installation described is not code compliant due to violations of NEC Articles 100, 250, and 450. These violations create significant safety concerns, including electrical shock and fire hazards. To rectify the situation, alternative solutions such as installing a new transformer with a true neutral and grounding system using a single-phase transformer with a secondary voltage of 240/120 volts, or installing GFCIs on each circuit should be considered. Consulting with a qualified electrician or electrical engineer is essential to determine the best solution for your specific situation and ensure the safety and compliance of the electrical system. The importance of adhering to electrical codes and standards cannot be overstated. These codes are developed by experts in the field and are based on years of experience and research. They are designed to protect people and property from the hazards of electricity. By following the NEC and other applicable codes and standards, you can significantly reduce the risk of electrical accidents and ensure the safety and reliability of your electrical system. It's also important to stay up to date on the latest changes to the electrical codes. The NEC is revised every 3 years, and these revisions often include new requirements or clarifications that are important to understand. Continuing education and training are essential for electricians and other electrical professionals to stay abreast of these changes. Furthermore, it's crucial to use only qualified and licensed electricians for all electrical work. Unlicensed or unqualified individuals may not have the knowledge or experience to perform electrical work safely and correctly. This can lead to code violations, safety hazards, and potentially dangerous situations. Always check the credentials of any electrician you hire and verify that they are properly licensed and insured. In addition to following the NEC and using qualified electricians, it's also important to practice good electrical safety habits in your daily life. This includes avoiding overloading circuits, using extension cords safely, and keeping electrical equipment away from water. By being aware of the potential hazards of electricity and taking precautions to avoid them, you can help prevent electrical accidents and protect yourself and your family from harm. The information presented here is intended for educational purposes only and should not be considered a substitute for professional advice. If you have any questions or concerns about electrical safety, it's always best to consult with a qualified electrician or electrical engineer. They can provide personalized guidance based on your specific situation and help you ensure that your electrical system is safe and compliant. The discussion underscores the critical role of proper grounding and bonding in electrical systems. Grounding provides a path for fault current to return to the source, allowing overcurrent protection devices to trip and energize the circuit. Bonding connects metal parts of equipment and structures together to create a low impedance path for fault current, minimizing the risk of electrical shock. When grounding and bonding are not properly implemented, it can create a dangerous situation where fault current can flow through unintended paths, potentially energizing metal surfaces and creating a shock hazard. Therefore, it's essential to pay close attention to grounding and bonding requirements when installing or modifying electrical systems. In addition to the specific code violations and safety concerns discussed earlier, there are other potential issues that can arise from the improper transformer installation. For example, the voltage imbalance can occur if the load is not evenly distributed between the two legs of the 240-volt supply. This can cause overheating of equipment and shorten its lifespan. Also, harmonic distortion can be introduced into the system if the load is nonlinear, such as electronic lighting ballasts. Harmonic distortion can cause overheating of transformers and other equipment, as well as interference with other electrical devices. These potential issues highlight the importance of carefully considering the load requirements and the characteristics of the equipment being powered when designing and installing electrical systems. The scenario presented serves as a reminder of the importance of thorough planning and careful execution in electrical work. It's not enough to simply connect wires and turn on the power. Electrical systems must be designed and installed in accordance with all applicable codes and standards to ensure safety and reliability. This requires a thorough understanding of electrical principles, as well as attention to detail and a commitment to quality workmanship. Furthermore, it's crucial to document all electrical work that is performed. This includes creating accurate wiring diagrams, labeling circuits and equipment, and keeping records of inspections and maintenance. Proper documentation can help to ensure that the electrical system is properly maintained over time and that any problems can be quickly identified and resolved. In conclusion, the improper transformer installation at the football field presents a significant safety hazard and violates several key provisions of the NEC. To rectify the situation, alternative solutions such as installing a new transformer with a true neutral and grounding system using a single-phase transformer with a secondary voltage of 240/120 volts, or installing GFCIs on each circuit should be considered. Consulting with a qualified electrician or electrical engineer is essential to determine the best solution for your specific situation and ensure the safety and compliance of the electrical system. The lessons learned from this scenario underscored the importance of adhering to electrical codes and standards, using qualified electricians, and practicing good electrical safety habits. By taking these steps, we can help prevent electrical accidents and protect people and property from the hazards of electricity. It's important to emphasize that electrical safety is a shared responsibility. Everyone who works with or around electricity has a role to play in ensuring that it is used safely. This includes electricians, engineers, contractors, building owners, and even homeowners. By working together and sharing knowledge, we can create a safer electrical environment for everyone.